So on the first day of this unit, we were talking about different kinds of energy. We talked about like nuclear energy, we talked about electrical and chemical and all of that. Okay, but as I said that first day, the most important type of energy for us in this unit is mechanical energy. And today we're going to look at the conservation of mechanical energy. What is mechanical energy and what does conservation of mechanical energy mean? So for the past week and a bit, we've been going over work and energy. And our definition of work was that work is a change in mechanical energy. Okay? Now, we have to look at what exactly is mechanical energy. So when energy is transferred to an object, it can cause a change in both the object's kinetic as well as potential energy. Both can change. We never did any problems where both changed, and we won't. Okay? But both can change when work is done. Okay? When energy is transferred to the object. So a ball thrown upward has kinetic energy because of its motion, but it also has potential energy because it's above the surface of the earth. Okay? Since kinetic and potential energy are so closely related in many situations, they are combined as a single type of energy called mechanical energy. So this stuff right here is super important. Okay? It is what mechanical energy is. So mechanical energy is the sum of an object's kinetic and potential energy. Okay, so we simply calculate it by adding those two things together. Okay, so EM equals EK plus EP, which would further be expanded to look like this: 1/2 mv squared plus mgh. Okay, that would calculate for me the total mechanical energy of an object or system. Okay, so if we have a kind of a simple example here with a baseball, okay, we throw this 0.300 kilogram baseball straight on a straight line through the air, 2.5 meters above the surface of the earth at 20 meters per second. Does it have mechanical energy? So I throw the ball, it's 2.5 meters above the ground, and it's moving at 20 meters per second. Does it have mechanical energy? Yes, okay? Because it has both kinetic, it's moving at 20 meters per second, and potential, it's 2.5 meters above the ground. It has both types of energy. Okay, everybody with me there? So if I wanted to calculate that mechanical energy, I would simply fill in this formula. So we'd start out with EM equals EK plus EP, put in the formulas, 1/2 mv squared for EK, mgh for EP, and then plug in our numbers. So 1/2 times the mass times the speed squared plus the mass times gravity times height. Right? And when we do that, we would get 67.4 joules of total mechanical energy. Okay? Now, can you actually throw something in a straight line? No. What does it always do? It always curves, falls down to the ground. Okay? It's what we call a projectile arc. So I can throw this thing, but it's going to do that. All things do. Okay? Gravity pulls them back to the earth. All right? Now, in that case, going from here to here, does the potential energy change? Like from there, from that height, let's say back to the ground, does the potential energy change? You get greater or less? Less, yeah. As it falls, its height decreases, so it has less potential energy. As it's falling, what happens to its speed? It goes up. Okay, so as it's falling, it loses potential, but it gains kinetic. That's the law of conservation of energy. Okay? It says that the mechanical energy here, the initial mechanical energy, will be equal to the final mechanical energy. All that's going to change is how much of that mechanical energy is potential and how much of it is kinetic. They can easily turn into one another. Okay? But the total amount of mechanical energy is going to remain the same. That sort of makes sense? All right. So this is that classic bow and arrow example that we talked about before. We're actually going to do a problem to do with that on the next page here in just a second. So what I'd like you to do right now, okay, is we're going to do a couple of problems like this one, where we just calculate the total mechanical energy, or we use this formula here. Maybe we're given the kinetic and the mechanical and asked to calculate potential. If I was given kinetic and mechanical, how would I calculate the potential? Yeah, subtract the kinetic, right? I mean, we're just algebra, right? We just have to manipulate a little bit. All right, I would like you guys to try 8, 9, 10, okay? These are the correct answers here on the right. Don't worry about these two numbers on the left. We're going to talk about those after we've done the initial part of those questions, okay? So copy them down, or actually, sorry, they're in your notes, I think, right? Okay, so just give 8, 9, and 10 a try. I'll give you a few minutes, and then we'll go through one at a time. Okay, so for the first one, for number 8, okay, we're told that the seagull is flying horizontally at 8 meters per second. So we were given the speed. Okay, we were told it's holding a clam that has a mass of 0.300 kilograms, because they gave it to you in grams. Okay. And it is 30 meters above the ground. Okay, so in this case, does it have mechanical energy? It does. Does it have both kinetic and potential? It does. It's moving and it's above the ground. So to calculate this, all we have to do is go mechanical energy equals EK plus EP. Okay, and so that'll be 1/2 times the mass, which is 0.3, times the speed squared, so 8 squared, plus 0.3 times 9.81 times 30 meters. Okay, if we punch all that into our calculator, we should get 97.89 joules worth of energy. Okay, so there we go. That's what it should look like. You can. Won't make any difference. Right? It's still going to do order of operations. It's going to do the kinetic, going to do the potential, then it'll add them. Multiplication division first, right? Okay. Questions on the first one? How many people have done number 9? Okay, I'm going to give you a little bit more time then to do number 9. Okay, on number 9, it's telling you the mechanical energy, and this, sorry, is hard to read. This is times 10 to the 3. So this is 3,000 joules. Okay, so it has 3,000 joules of mechanical energy, and they tell you the speed at which it is moving. They want you to find the potential energy of the athlete. Okay, so remember, the formula we're using is this one. And we're looking for the potential energy in that particular question. So with number 9, okay, we know the mass. They tell us it's 55 kilograms, okay? And they tell us it's a high jumper who leaps into the air, okay? At the top of the leap, the athlete has a total mechanical energy of 3,000 joules. So they told us EM is 3,000 joules, okay? And they're moving at 8.33 meters per second. Okay, so with M and V, can I calculate their kinetic energy? Okay, they want me to calculate the potential energy. Right? Well, if I have enough information to calculate EK, and they gave me EM, all I have to do is take this formula and manipulate for EP. So how do I get EP by itself? Right, subtract EK over to the other side. So we'll have mechanical energy minus kinetic energy equals potential energy. I mean, that makes sense. If I add those two things together, I get mechanical. So if I take mechanical and subtract one, I should get the other. So when I'm plugging in my numbers here, that's going to mean I'm going to go 3,000 joules minus 1/2 times 55 kilograms, okay, times 8.33 squared. Okay, so all I did was this, guys. I went mechanical energy minus 1, oh, not equals, minus 1/2 mv squared equals EP. Okay, so that's what this is right here. Okay, so when I punch all that into my calculator, so 3,000 minus 0.5 times 55 times 8.33 squared. Okay, so 1,091.8 joules. So I think what we had up there, right? 1,091.8 joules worth of potential energy. Okay, that's not where I would stop that question. I would ask you, how high is the bar? Since you just calculated the potential energy, could you calculate the height of the bar? Okay. Well, this number that we just calculated, this 1,091, so we said EP equals 1,091.8 joules, okay? Does that number equal m times g times h? Do I have the mass and gravity? I do. The question gave me that. Well, we always know what gravity is. Okay? So all I would have to do is go divide this number by m times g, and I'd be left with the height. Okay? So if I take that 1,091 and divide it by 55 times 9.81, we'd be looking at 2.02 meters, which is 6.5 feet roughly. Okay. I coached track for 20 years. I can count on one hand the number of times I saw a high school athlete go over 2 meters. Okay. That's a pretty impressive jump. Right. Usually by the time somebody gets around 2 meters, everybody's standing around doing the unison clap, okay, waiting for them to go over. That's an impressive jump, 2.02 meters. Right. That means you jump over Barrett.
I can jump over.
He has to be standing up. Okay. All right. Does that one make sense, how we would do that? Because that's where we would head to next, is instead of asking you just to calculate the potential energy, they'd ask you to calculate some part of that potential energy. Okay, I want you guys to try number 10 and see how you do with that one. Okay, so we're dropping a hammer from the roof. When the hammer is 50 meters above the ground, it has 1,880, that's what that number is there, 1,880 joules worth of mechanical energy. Calculate the kinetic energy of the hammer, and if you can, how fast it's going. Okay, I'll be satisfied with just kinetic energy of the hammer, but if you can go that step further, good. Okay, let's have a look at number 10. So in number 10, they tell us the mass, it's 2.00 kilograms. Okay, and they tell us the height, 50 meters, okay, and they tell us the total mechanical energy is 1,880 joules. Okay, we're looking for the kinetic energy of the hammer. So we're back to this formula, mechanical energy equals kinetic energy plus potential energy. Okay, I want to calculate kinetic, so what do I have to do with EP? Subtract it over to the other side. All right, so I'm going to have mechanical minus potential equals kinetic. All right, so that'll be 1,880 joules minus 2 times 9.81 times 50. 1,880 minus 2 times 9.81 times 8. No, times 50, sorry. Okay, so 899 joules worth of kinetic energy. Okay? Everyone all right with that? All right, what if the question didn't ask me for that, but asked me for how fast it was going? Could I calculate that? Absolutely. Okay, and actually I could do it even from this step right here. If I was at this step and I had EM minus m times g times h equaled 1/2 mv squared, right? I'm saying the same thing here. If I wanted to get v, I just divide both sides by half of m. then square root. I could solve for it directly. Or I can just take the number I just calculated, 899, and divide by half of m and square root. That'll also give me v. It's the same thing. Okay. So if we do that, okay, so 899, so square root, answer divided by, I should have just put 1. I should have put nothing. Okay, it's 29.9 or 30 meters per second. You would not want to be standing under that hammer. It would hurt a lot. Okay. All right, does everyone understand how the EM equals EP plus EK formula works? Okay, so we're going to walk through this one together just to kind of illustrate a point about work energy theorem and how it relates to what we're doing now. Okay, so if I use an average force of 100 newtons to pull back a bowstring half a meter and aim the bow vertically, which is an example we went over a bunch of times, okay, what's the work done on the bow? Okay, how do I calculate the work if I was just given force and distance? Multiply them together. I have force, I have distance. 100 times 0.5 is 50 joules. Okay, how much potential energy is now stored in the bow? $50 joules, exactly. I don't have to calculate anything. I already did all the calculating necessary. Okay? If I did 50 joules worth of work, the bow now has 50 joules worth of energy because it's what I did the work on. Okay? How much kinetic energy does the arrow have the instant it's released from the bow? 50 joules, because now the bow is going to do work on the arrow. It's going to transfer all of its 50 joules of energy to the arrow. Okay. What will the potential energy of the arrow be at the highest position in its flight? Its kinetic would be 0 at its highest position. When you shoot something up in the air, it goes up, 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 but it goes slower and slower and slower and slower until it reaches its maximum height where it stops for an instant. It only has potential energy there. How much? $50 joules. That's all it can have. Okay? It can't have more than that. It only got 50 joules from me, from the bow, from the kinetic to go upwards. Okay? It's going to have 50 joules. Could I calculate its maximum height? Yeah, pretty easily. That's stuff we were doing last week. Okay? All right. Does that make sense? So work energy theorem goes along with conservation of energy. It says that energy cannot be created and it cannot be destroyed. Okay? So once the work is done, that energy is in the system and it will always be in the system. All it's going to do is turn from kinetic to potential and back. Okay? So that arrow, as it's going up in the air, starts out with 50 joules of kinetic, and its kinetic slowly turns into potential. Okay? And then that potential, when it falls back down, turns back into kinetic. That's how a roller coaster works. Okay? The chain lifts the car, carries the car up to the top of the roller coaster. That's all the work. Once it gets there, that's the most energy it will have. Okay? If it was a perfectly frictionless roller coaster, right? That amount of energy it has at the top would be the amount of energy it has everywhere. Any point on the roller coaster, same amount of energy. If, again, it was in the perfect physical world and it was totally frictionless and it didn't lose any energy along the way. Okay? In actual fact, roller coasters lose tons of energy, okay, along the way to friction and things like that. That's why they're so loud. That's not from the people screaming. Okay? They're even louder if there's nobody on them and they're just running them to test them. They're really loud. Okay? And loud means friction. All right. So, we already did those ones. Okay. So, law of conservation of energy says that energy can't be created and it can't be destroyed. The total amount of energy in a given situation remains constant. It can be converted from one form to another, but the total amount will never change. Okay? So the total amount of mechanical energy is always the same. In the absence of outside forces, kinetic can be converted to potential, as we said before, and back. Okay? So let's look at this example right here. Okay, I have a 1.5 kilogram rock. I think I have it on the next one here. Okay, a 1.5 kilogram rock dropped over the edge of a cliff 30 meters above the surface of a lake. What's the speed of the rock just before it strikes the surface of the lake? Okay, what are our givens here? Mass. Okay, what else? Height. Initial or final? Initial. What's my final height? Zeros, yeah. What's my initial speed? 0, because it's being dropped. And the question's asking me to find the final speed. Okay, did we write down a lot of numbers? Oh, sorry, that's supposed to be unknown, sorry. Did we write down a lot of numbers? How many of those were actually written out as numbers in the question? 2. The rest of it we had to get from the context of the question. I had to understand it because it's dropped, that means its initial speed was 0. Okay, and that at the end of the question it's hitting the surface, that means its final height is 0. It never told me those things as numbers. Okay, the question made me have to infer them, right? And that's part of doing a law of conservation of energy and work energy theorem question. All right, so this is the information that I have. The law of conservation of energy tells me that the initial mechanical energy and the final mechanical energy are equal, because energy can't be created and it can't be destroyed. All that can happen is potential can turn into kinetic and kinetic can turn into potential. So what I want to do next is expand this out. How do we calculate mechanical energy? We just use this formula in the last bit. That's how I calculate kinetic energy. I add them together, right. Okay, so I'm going to take my potential initial and add it to my kinetic initial. On the other side, I'm going to have the same thing, except the I's will be F's. Okay, am I still saying the same thing? Am I still saying initial mechanical equals final mechanical? I am. I've just expanded it out. Okay. Are any of these energy types 0? Which ones? Final potential, yeah, because we're at a height of 0. There's one more. Initial kinetic, yeah, okay. We're dropping it, so we're not moving at the beginning. Okay, so that simplifies this a great deal. That just means all my energy, all my mechanical energy initially is potential, and all my mechanical energy at the end is kinetic. Okay, now, do I have formulas for those two types of energy? Okay, have I changed what I said initially yet? I have not. I'm still saying my initial mechanical energy equals my final mechanical energy. I've simply identified that at the beginning it's all potential, and at the end it's all kinetic. All right? Now, I want to calculate VF. So what do I have to do with the half and the M? You guys were doing this last week, no problem. What do I do with the half and the M if I want to get VF by itself? Divide them over to the other side, yeah. Okay, I got an M on the top and an M on the bottom. I got no addition subtraction operations. What can happen to it? Yeah, I can get rid of it. It cancels. Okay. If you don't like that, just put in 1.5. It'll still work. Put in 1.5 for both ends, and it'll still work. Okay. Now that solves for VF squared. I just want VF, so what do I have to do? Square root it, right? Okay, this is just like what we were doing last week. Okay, so that's going to be the square root of GHI divided by 1/2. Okay, so we're 30. Okay, so it was dropped from a height of 24.3 meters. Or sorry, no, sorry, it was dropped from 30 meters. It's going to be moving at 24.3 meters per second. Sorry. Okay, so the final speed of the object will be 24.3 meters per second. Okay, what if instead of being dropped, someone threw it downwards? How would this question change?
The initial speed could change.
Right, the initial speed would be different. There'd be a value that's not 0 for it, which means it would have more mechanical energy, which means at the end it would be going even faster, right? Okay, because it would have this initial kinetic energy in addition to the initial potential energy. All right, you know what? I'm going to give you guys a quick break here and then we'll try these two. All right, let's have a look at number 11. So on number 11, okay, again, how do I know that this is a law of conservation of energy question and not a work energy theorem question? Like just from the context of the question, how do I know?
Because of the givens we have.
Yeah. Are you told force or distance? Okay. So if you're not given force and there's no mention of work or any change in energy, it's a conservation of energy question. Because a conservation of energy question results in no change in energy. Okay? So if you see the word work, or you're given force, or there's any mention of a change in energy, then it's a work energy theorem question. Okay? But if it's a conservation of energy question, it's not going to give you force. It's not going to mention work. Okay? And there's not going to be a change in mechanical energy. All right, so initially, we're dropping the water balloon. So we'll set this up like we always do. Okay? Initial potential plus initial kinetic equals final potential plus final kinetic. Now, two of these are 0. Which two?
Speed.
Initial speed, so as a result, initial kinetic. And what else? Not initial, final potential, yeah. All right, so those two are 0, so now I'm down to this. The initial potential becomes the final kinetic. They're equal. Okay, so now I can put in the formulas. M times G times H initial equals 1/2 mv initial squared. Okay, again, what can happen to the m's here? They can cancel. It's in every term. In fact, even if these were not 0, if they both had numbers, we could still cancel them. Okay? If something is in every term in an equation, every term is multiplied by it. So you can cancel it. Okay? All right. So I'm going to cancel the m's because I don't want to move more than I have to. Okay? As I get older, I realize doing more work than you have to do is silly. And it hurts. For you, when you're young, do more work than you have to. It's good for you. Okay? All right. Life lesson. That's totally not related to what we're talking about here. I'm trying to find sorry, this is supposed to be VF. I'm trying to find VF. So I need to divide both sides by 1/2 and then square root. That'll leave me with VF. Okay, so VF will be the square root of 9.81 times 12 divided by 1/2. Okay, 15.3 meters per second. All right, everybody okay with that one? Okay, now the last one asks you to calculate something else. So this is a kid on a trampoline. As the trampoline is throwing them up in the air, okay, so at the moment they're gonna leave the trampoline, they're at ground level. So this is one of those trampolines that's like built into the ground, okay, not one that sits above the ground. Okay, so built into the ground, okay, and just at the moment they're gonna leave the trampoline and get thrown into the air, they are moving at 1.6 meters per second. Right? You need to calculate the height, the maximum height they will reach. How fast will they be moving at that maximum height? 0. That's the trick to this question. We have to recognize that when you're at your maximum potential and your maximum height, you have no kinetic. All right, I'll give you a few minutes on number 12. All right, so on number 12, okay, we're still going to start out with this whole EI equals EF thing. Okay, the energies are going to be equal. And we're going to go to this. Initial potential plus initial kinetic equals final potential plus final kinetic. In this situation, it's reversed. We're starting off with kinetic energy and ending with potential. Okay, so our initial potential energy is 0 because we're at ground level on the trampoline about to be thrown up into the air. Okay, and that means that our final kinetic is also 0 because at our maximum height, we have no speed and thus no kinetic energy. Okay. So now that we've got that sorted out, now we can say 1/2 mvi squared equals m times g times h final. Okay, so if I'm looking for h final, the first thing I'm going to do is cancel the m's, and then I'm going to divide by g. All right, that'll leave me with hf. So hf will be 1/2 times 1.6 squared divided by 9.81. Okay, and we're going to get 0.13 there, but put it all in. 0.5 times 1.6 squared divided by 9.81. 0.13 meters. About that far. It's a little kid. It's a little kid. See, 30 kilograms. Okay? Kid's only about 60 pounds. Little kid. Okay? All right, fine. It's a lousy trampoline. Whatever. Have it your way. Okay? Yeah, it's not very far. It's not very high. Okay? But 1.6 meters per second is also not very fast. So that might just be you're kind of like bouncing up and down a little bit on the trampoline. Okay? You're certainly not jumping vertically into the air. That's a bit of a stretch. Okay. All right, does that one make sense? Okay, they generally all work this way. They get more complex. We're going to do some where the potential and the kinetic, there's values for all four. Okay, all that changes is that you have to subtract some things before you divide, but it doesn't really change the principle of it. Yep. Okay, we already did that.
Oh my god.
Okay, I would like you guys to try number 14. Okay, so number 14 is a pendulum. I'm going to get out my ghetto physics pendulum here. Okay, this is saving taxpayer dollars like you wouldn't believe. Okay, so this is how a pendulum works. Okay, to get it going, I have to lift it over here. What have I just done? No, I didn't stop it. It wasn't moving to begin with. I put potential energy. I did work. Okay, I put potential energy into it. Now, if I let it go, that potential energy keeps converting into kinetic and then back into potential and kinetic and into potential. It just keeps doing that. Okay, it's the law of conservation of energy. It'll just keep doing this, converting potential into kinetic back and forth, back and forth. Okay. All right. So I want you guys to give that one a try. There's one piece of information in that question that is a distractor item. Okay, there's one piece of information it's giving you that is completely unnecessary.
What's the strength?
The string, the length of the string. Okay, all that matters is how far up from its lowest position I move it. That's what gives it potential energy. Okay, I could do that with this length of string, or with this length of string. Doesn't matter. Okay, I can move it up 10 centimeters from its lowest position, regardless of how long the pendulum is. All that changes is, okay, how long it takes the pendulum to swing. All right, give number 14 a try. Okay, we'll give you a bit of time there and then we'll go over that one. So in this one, we have the mass, 500 grams or 0.500 kilograms. Not that it matters, it's going to cancel anyway. Okay, and it's suspended by a 50 centimeter string. Don't need it. Okay, the ball is pulled horizontally up a total of vertical distance of 10 centimeters. So our initial height is going to be 0.10 meters, because it has to be in meters. At the bottom of the arc, the mechanical energy of the ball was determined to be 0.491. So, joules. Okay. What's the speed of the ball at the bottom of its arc? All right, so this is the mechanical energy. This is the initial height. Okay. If this is the mechanical energy, can I really simplify this question? What kind of energy does the ball have at the bottom of the arc? It's all kinetic. So is this how much kinetic energy it has at the bottom of the arc? Yes, it is. I don't have to do this whole EI equals EF thing. I'm kind of doing that. Okay? I mean, sure, I can write this out and say EI equals EF, but if that's the case, that number is both of them. Would you agree? So I don't have to go through this whole thing here where I go M times G times H initial equals 1/2 MV final and do all the manipulating. I could, I'll get the same answer, but why? They told me the mechanical energy. They said it's this much. I don't need to go any further than that. I just need to manipulate this to get VF. Okay, oh, sorry, that was squared, so that'll cancel the square. And if I do that, I should still get my 1.4 meters per second. Okay. Everybody all right with that idea? It would have been fine to do it the way we've done all the other questions. It's just more work. Okay, this is one of those questions that is, if you really understand this, you might recognize that there's a shortcut. Okay, where you can kind of apply what you know and go, oh wait, they told me what the mechanical energy is. I can shortcut this question because I already know what the total is. All right. What about a pendulum here? I want you guys to write this one down. Okay, so we have a sledder with a mass of 70 kilograms at a point that is 30 meters above the bottom of a hill, vertically. Okay, they're moving at 1.5 meters per second, so they've kind of done the run up and they've jumped onto the sled, and now they're going down the hill. Okay, how far above the bottom are they when their speed is 7.5 meters per second? I'll give you a minute to write that one down, and we'll walk through this, and then we'll call it a day. All right, let's have a look at this one. So it's a law of conservation of energy question. So it's an EI equals EF question because there's no mention of any forces and it doesn't talk about work or anything like that. So we know we're starting off with EI equals EF. Okay? What I have to figure out is, do I have all of these? So initial potential plus initial kinetic equals final potential plus final kinetic. Okay, this is always true. Sometimes we can cancel some of those because they're 0. And to this point, we have. In this question, they're 30 meters above the ground at the start. So do they have potential? Yes. Okay. They're also moving at 1.5 meters per second. So do they have kinetic? Yes. So they have both initial potential and initial kinetic. All right. At the end, there's some unknown height above the bottom. So it's probably not 0. Would you agree? They probably wouldn't make me calculate this if it was going to end up being 0. Okay? So yes, we definitely have some final potential energy. And they're moving at 7.5 meters per second, so that means, yes, in fact, we do have final kinetic as well. None of these are 0 this time. They all have a value. Okay? What I'm looking for is going to be part of which one of these terms? I'm looking for the final height of the sled. Which one of those terms will that be part of, Ethan?
Energy potential final.
Right, the final potential. So what I'm going to do right now, before I do anything else, is I'm going to isolate the final potential energy. How do I do that?
Subtract final kinetic.
Right, subtract the final kinetic. So I'm going to be looking at initial potential plus initial kinetic minus the final kinetic equals the final potential. Okay, now I'm going to expand that out. Now I'm going to put in all the formulas. So m times g times h initial plus 1/2 mv initial squared minus 1/2 mv final squared equals m times g times h final. Okay. Are we doing anything really different than what we've done before? Not really. Okay, it's just that none of our stuff was 0 this time, so we actually had to pull things over as opposed to cancel them off. What variable is in every term? M. What can I do with it? Yep. If you don't feel comfortable doing that, you can leave it in. Okay? They did, after all, tell you what it was. Here's the problem. Sometimes I make up a question like this and I don't put the mass in. I forget. I'm old. Okay? But in the end, it doesn't matter because you don't need it. Okay? This only happened once, but I forgot to put it in on a test. Okay? Most people just went about the question no problem because they realized they didn't need it anyway. But I had a person who came up to my desk and they're like, Mr. Coderre, I think you forgot to put the mass of the roller coaster in. I'm like, oh, yep, you're right. It's 500 kilograms. Back to the desk they go. Okay? Then another person came up. Mr. Coderre, what's the mass of the roller coaster? And I couldn't remember what I told the first person. I'm like, 800 kilograms. And I looked out at the class and there were like 3 people out there whose eyes just became like dinner plates. They're like, oh God, he told them 2 different numbers. And I realized what I'd done. And then I decided to have fun with it. Another person came up. 200,000 kilograms. It didn't matter, you punch in any mass you want, it's going to get the right answer. Okay, I could say any number. And then I realized that was really mean, and I just said, guys, remember the mass doesn't matter, but you can put in whatever number you want for M. You decide how heavy the roller coaster is. Most people were just chuckling at that point because they realized they didn't need it. Okay, so we don't need it. We're going to get rid of it. Why move stuff if you don't have to? All right, I want HF by itself. What do I have to do with G? Divide both sides by G. Okay, now we're solving for HF. We just got to plug in our numbers. 9.81 times 30. So there's my initial potential. Plus 1/2 times 1.5 squared, my initial kinetic. Minus 0.5 times was 7.5. My final kinetic equals HF, divided by 9.81. Okay, so if I punch all that into my calculator, 9.81 times 30 plus 0.5 times 1.5 squared minus 0.5 times 7.5 squared divided by 9.81. Okay, they haven't gone very far. They're only 3 meters lower than they were at the start of this question. Okay, which makes sense. They haven't gotten that much faster either. They went from 1.5 to 7.5 meters per second. Okay, so 27 meters will be our answer there. Okay, so we'll be working on that a bit this week. Here's the plan going forward. Tomorrow and Wednesday we'll be working on conservation of energy. Thursday we're going to do a lab on conservation of energy. Friday I will do the unit exam review for this unit. Right? Monday we'll be looking at Oh, right, we don't have school Monday. And I made the exam Wednesday, right?
Yeah.
Yes, okay. So Tuesday, we'll look at efficiency, which takes no time at all, okay, and then Wednesday will be your test. Thursday, the 26th is Thursday? Then we might start the next unit before that, on the Wednesday. So, okay, basically we'll be done the unit by the end of this week, minus efficiency, which takes like a half a class. Yep.
Yeah.